Welcome, everyone. Pleasure to be here, and thanks for you for being here. Thanks to ADC for having me. Last night I had a dream where I passed out during the introduction, and we've already gotten past that, so we're on a good track to a success so far. So, my name is Esa Jääskelä, and I will be talking about unit testing the audio processing software. And a few words about myself. I'm from Oulu, Finland, the northern part of the Northern Europe. And I work as an embedded software developer at a company named Bumble. And they were kind enough to pay my trip here and even for a return ticket. So I assume they're expecting me back on Friday. So my first talk, fortunately not my first time of doing this exact presentation, although yesterday after ADC quiz I added few slides, so let's see how good those ones were. So as mentioned, I'm an embedded software developer by profession, and I mostly work with bootloaders, kernels, drivers, other such kind of low-level things. Occasionally I solder some bits to CPUs, but what I really like to do as well is music. And as witnessed in this picture where I'm holding a big guitar with 4 strings and wondering why it makes a low sounds, almost like a bass-like sounds. And in the end, I ended up becoming an hobbyist audio programmer in a desperate attempt to combine these two interests of mine. That's, I suppose, quite common path how people end up here. So basically, I make music and I want to learn how to make the tools that make music. And I got involved in VST programming, started Googling out things, tutorials, found the audio programmer tutorials, encountered JUCE, and finally realized that if I really want this thing to do what I wanted to do, I need to learn maths as well. And at this point, I want to mention that I have a bit of a bias toward JUCE because I have been using it mostly during my audio development things. So things apply outside JUCE as well. So, but the terminology may be borrowed from there. So I started audio programming, made my first plugin. It was called delayed audio, and it worked quite well in the beginning. There was just one tiny problem. It was really horribly optimized. When it was idling on my laptop, I think it used 5% of the CPU on Ableton. So after that, it was a good thing to try and optimize and refactor it. And I started doing that. And it went well, renaming things, optimizing things, and so on. And compiled it, tried it, and no sound anymore. So things went bad. And I spent a bit more time than I want to admit, trying to figure out what went wrong and where. And in the end, it turned out I was clearing buffers a bit too often, practically all the time. But that happens when you're starting out. And but still, this was the way I progressed. Basically, compiling, shouting into a mic a few times, and hoping that you get some sort of audio back. And for a while, I progressed like this. But I think there should be some sort of a better ways because. This is really difficult way of, first of all, this is low to do things like this, and then it's difficult to do things like this. So I started to think about back to my student times and remembered the mythical word of testing, and especially automated testing. How many of you were in the Focusrite talk yesterday? Few. Yeah, wonderful. I think they really nailed the point there that the best way to make testing interesting is with the dad jokes. Unfortunately, I didn't prepare any, but yeah. So, but this is a beginner-friendly walkthrough of what unit testing is and some special considerations for audio unit testing. And getting started with it, and in the end, some practical examples. So perhaps a bit easier to digest a lecture after the lunch as a dessert. So let's start. The unit testing, it in short, means running small testable pieces of code and verifying that they operate well, or as you'd expect. Focusing on verifying the inputs and outputs that go to the system. Basically, you feed something to the system and check that your expectations are met. Whether that would be return values, function call traces, or what have you. But there's a commonly used excuse. Audio software is different and it can't be tested. And you need ears for testing. You need to hear what's happening. And in a way, that's true. I agree to a certain extent. And the inspiration for this whole exercise also came from a friend of mine who said that, why don't you put unit testing to it? And this is exactly what I thought. It's audio software, you don't test it. A bit naive thing to think. Not a bit, it's a really naive thing. But I started a new project after the delay, and I thought that why wouldn't I do the things the right way? And started investigating unit testing the audio. And indeed, audio signals are digital information and can be tested like anything else. So if you have a sine wave, it's basically an array of values ranging from, well, depends what they range from the type of container, but for example, -1 to +1. And I have mostly done VST and music software programming in this audio development context. So again, this is another thing that may affect the way I talk about things, which comes into play a bit soon. But regarding this sine wave, we know that it is sine wave and it's always like that, but the outputs of the functions may not necessarily always be like this. They may not always be this predictable array of floating point values. And I made this sort of table where we can think about how to sort of approach this testing. This is the idea that I use myself when testing. So we have known inputs and known outputs in the test. Basically, this is the traditional case of unit testing, where you feed something to the system and check the expectations. Then we have the known input, but semi-known output. So, for example, if we have a filter that applies some character or color or secret sauce to the signal it receives, it may not always be fully known if there's some random component introduced to it, like noise or other kind of non-deterministic variable. Then we have semi-random inputs on the right. I'm not going to focus on those because those are more like fuzz testing, and that I think that would warrant a whole another talk. But we're going to focus on tests that have known input and how to verify their outputs. So the first thing to do, of course, is to create a plan. Create a plan that what you want to do or need to do. You don't always want to do what you need to do. But basically identify what needs to be tested. So generators, processors, parameters. So if you have a like sine wave generator, you want to test that. If you have a processor like a filter, you want to test that. And then you have parameters to control those. You want to test those as well. You basically want to test everything you can. This is not an exhaustive list. There are definitely other types of components as well, like user interface and so on. Then recognize inputs and outputs for these items. So, for example, generators, they can be MIDI signals, and outputs are the audio signals. For processors, they can be, input can be audio signal, and output can be audio signal. You know, it depends on what you're testing. And then recognize the known and semi-known outputs in this kind of system. So if you have a sine wave generator, you know what to expect. You want the sine wave. You don't want anything extra. You don't want the useless artifacts that may appear. You don't want any noise. You want the exact sine wave that you've given to it with certain parameters. But on the other hand, if you have a noise generator, you know that you want to receive noise, but you don't exactly know what the noise sounds like because it's inherently random. There are different types of noise, so you may know roughly what the noise sounds like. Like white noise and brown noise, those sound different. And these semi-known outputs may not always be apparent, like the earlier mentioned filter that adds some color to the audio. So it may seem obvious that the filter just filters, but it always doesn't. And this raises the question that how to verify these non-exact outputs. There are basically two approaches to this. Either remove the randomness to make the outputs always exact, or embrace the randomness. And for example, you can remove the randomness in testing by using a fixed seed, and you end up with a situation known as displayed in this classic Dilbert comic. So, yeah, you can never be sure, but this kind of testing is a bit dumb because it always tests the exact same thing. You're not going to uncover anything new by this type of testing. So to continue, you can remove the randomness by atomizing your tests, making them into smaller, even smaller and smaller units. So, for example, again, talking about the filter example, you can separate the filter and the color from each other. And that's good. That way you can verify the filter, but you still have the random component. What do you want to do with it? So at that point, some kind of fuzzy matching with thresholds can come to play. And to do that, we get to fast Fourier transforms. So Fourier analysis converts a signal from its original domain of the time and space to a representation in the frequency domain and vice versa. Sentence straight out of Wikipedia, but I suppose most of the people here know what this means. Commonly used in all kinds of signal processing. For example, as mentioned earlier, I have the background in embedded software development, and I encounter this often in radios and such, so it's not exclusive to the audio domain of things. But as a visual format, you have this kind of sound. You have no idea of its characteristics, except that it's quite loud, and it lasts some time. I apparently cut it out the time scale of the picture. But you can feed this to an FFT function. Copyright-free wizard appears and give you the spectrum domain image, or sorry, frequency domain image, or spectrogram. And I think the line is quite thin, so it may be a bit difficult to see in person here. But basically what we can now see that the earlier mysterious audio is indeed a sine sweep going from 20 hertz to 20,000 kilohertz. And yeah, we can, with the FFT, we can get the characteristics of the audio. And yeah, the FFT divides the audio into frequency bins. So basically, when you look at the picture, you can see that the signal is divided according to the resolution to, I think, 1024 frequency bins in this case. And we can then compare these values instead of the time domain sample values to get a bit more fuzzy matching, to test out the characteristics of the audio instead of the raw sample values. I also added this picture to explain a bit what Fourier transform does. Basically, it's based on the idea that every signal can be represented as a sum of other signals, and that way we can get the frequency domain representation out of the time domain representation, or spectrogram out of the waveform image that we saw earlier. So now that we know everything that we need to know, let's program and try to make some tests. No, let's move towards slightly more practical topics, I hope. So after failing with the delay plugin to make it work, it was a bit miserable, a bit frustrating situation. So I tried Googling to help me get started with this new testing thing. And I found this JUCE's unit tests, and I gave them a go. And while JUCE is a good audio framework, I don't think it's a good unit testing framework. So after giving it a short attempt, I couldn't do what I wanted to do with it. So I was back into this situation. And after Googling a bit more, I came across Google Test. And that was, of course, another way of integrating that was a full-fledged unit testing framework that I tried to integrate. And it got a bit weird. There was some patched version of Producer that was mentioned, and plenty of other things that had to be done to get that integrated. And in the end, I didn't get it working either. And then there was pain, lots of it. And this was sort of the reason why I wanted to do this talk, to hopefully give a bit of an idea on how to start with it. And because this wasn't quite as apparent I was hoping it to be. And I finally, after some Googling, I found the super useful template called Bumble Juice. Not my work. I want to stress this, that I take no credit for this. But Bumble Juice is a template for creating and building JUCE plugins in 2022. And it's created by Sudara. And it's definitely a super useful approach of doing this. So basically, it allows JUCE development with CMake. And if you're not familiar with CMake, you can think of it as a project or build definition tool. And basically what it does, it replaces Producer with CMake. And I personally like that because I use CMake at my work, and it's a more widely used tool, so knowledge of it is definitely useful. But more importantly, it integrated Catch 2 support. So somebody could do it what I couldn't do, and that was a highlight for me. And it allowed the easy integration of unit testing. It also provides GitHub actions, so you can automatically make your tests fail after every commit. And all in all, a super useful template. I definitely recommend giving it a try, if you can. Migrating existing projects may be a bit tricky. I'm kind of hoping to, at some point, write a converter from Producer to CMake, because in embedded JUCE development, you kind of have to have the JUCER file. So I'm a bit forced to work with both. But I hope that one day there will be some tool to convert between the two. Then, next topic. In brief, Catch 2 is a unit testing framework for C++, as good as any. Easy to use, no external dependencies. You can actually use it as a single header, so you can even skip the documentation if you want. And it's being actively developed. It's constantly getting updates, so I recommend giving it a go. And yeah, perhaps no, not yet. So after finding this useful template for my project, I got to work. I made a new project of the template and starting implementing something from it. And I came up with this filter unit test repository that is an example repository of Bumble Juice. And this focuses on the unit testing side of things. It's a super simple high-pass filter made with JUCE's internal ladder filter class. And there are some example unit tests created for it, and then there are some unit test helpers created for it. And I have to warn you, the code maturity isn't quite there yet, so it will definitely change in the future, hopefully this weekend. And I'm kind of hoping also to move the code helpers to a separate library, because currently it's basically part of this filter unit test repository project. So having them as a separate library to import to your project would definitely make it a lot easier to do. So finally, let's program a bit. So I have prepared a few example test cases to show how the syntax looks like and what kind of approaches we can take to the unit testing. So the simplest test of them all is, of course, always the hello world tests. And there is this get the name of the program tests, which is the simplest way of ensuring that things are hooked up correctly. So you can create your audio processor class, you can use it functions, and you can get something sensible out of it. So in case this test fails, you know you have broken something really important. And this test is part of the Bumble Juice out of the box. And let's see. I'll drag this over there and hope that I can see. Almost. So, yes, perfect. So, first, on the first line, we have to mitigate the possibility of demo effect. I have commented out all the test code, and I will be revealing it or commenting it in a few blocks at a time. And I have also pre-compiled the test suite. So nothing can possibly go wrong here. But let's look at the first test case that we have here. Basically, it's the filter instance name demo. And we can hopefully see, yes, one line of code where we create our plugin processor class instance. And then we simply just check that. Use the catch tools, check that matcher to ensure that the name that gets returned is what we are expecting. And with a simple test like that, we can get at least some level of confidence that we have actually integrated the unit testing framework to our project. The test case syntax itself is fairly simple. First, you have the test case macro, then you have the test name, and then you have the tag for the test. So if you want to run a certain group of tests, you can do it like that. So let's see if I can get this actually running. what was the name? Filter instance name demo. No, it wasn't. Sorry. Plugin instance name demo. Oh. I wonder how you can see anything if I cannot see, and I'm this close. Sorry, but I'll increase the font size a bit. As soon as I find my mouse. Oh, what happened? Well, nothing too serious, I suppose. So, the first, as you can see, well, this is a good learning experience because there's no failure case. I cannot increase the text size, but at least the contrast is better. So, sorry, I'll actually clear that and run it again so that we can actually see. So, we can see that the filter actually ran the one single test that we wanted in this case. And the randomness was seeded to a certain number. And as discussed earlier, we want to use a varying seed in the random, to allow a bit more variety in the testing. And then we can see that all tests passed one assertion in one test case. So as you remember, there was the one check of the name, and that passed very well, as expected. So we can now say with quite a lot of confidence that we have actually integrated the unit testing framework to our project. Wonderful. Now we can actually do some testing. So let's return here. Yes. And so actual functionality test, and where we test the audio processing function that we have, or the filter, because as mentioned, the filter unit test repository contains of a simple filter, high-pass filter, that filters audio signal. And with this test, we attempt to verify the core processing functionality of the software. And there are a few different ways of approaching this. If we have already well-defined filter that doesn't vary in the development, that doesn't have any random elements to it, we can actually just make a buffer comparison directly. And just compare two buffers, ensure that they match, and we get what we want out of the system. Assuming, of course, also that the input is constant. Or then we can take another approach where we try to figure out the characteristics of the filter and then try to build a test case from there. So if we, for example, in this case have a high-pass filter, we want to ensure two things. That there is no lower frequency content or lower end content in this output, and that we can also add an extra check that the total energy of the output decreases because there should be less content, assuming there's no gain. Of course, this doesn't have gain. I should have maybe mentioned that earlier. And yeah, I'll show a bit of a rundown of these two. Both of the two approaches. So let's start from here. I'll actually try to... Does it help anything to make it bigger? Maybe a bit. So the second test case, which is the filter processor demo. First, we define a few variables. Basically, samples per block and sample rate. So how many samples we process at a time and at what sample rate. Then we create once again, we need to create our plugin processor class. And then we read a SignSweep file. And if you remember, SignSweep is this narrow sine sweep that sweeps through the frequency range. And this is really useful tool in unit testing because it's a constant and it goes through the whole, it goes through the mostly audible frequency range. So you can get a bit of confidence on how it sounds on both low end and high end. Yeah. Then we create a new buffer, or sorry, read it to a buffer, create a copy. Yes, here we create a copy. And then we calculate how many chunks we want to test, basically dividing by the amount of samples with the samples per block so that we get the number of how many times we need to call the processing function to process the whole sine sweep. Then we create a MIDI buffer because it's expected by the process block function. Then we call prepare to play. This, if you've used JUCE, this is really familiar to you most likely. So I scroll up a bit, and then what happens next is that we go through the sine sweep one block by one block at a time, and then feed it to the process block function, and then store it back to the buffer that we started from. So this way we can process the entire sine sweep signal and get output of it stored back to a buffer. Then what happens next is that we check. This is a custom matcher that I wrote for this project. So it checks that. I'll put it a bit higher so everybody can see. It checks that the buffer that was just processed doesn't have higher energy than original buffer. It should have less or equal, but it cannot have higher energy than the original buffer before processing. Yeah, makes sense. And then this is another matcher I wrote for this project. Basically what this does, it creates an array that has the length of the amount of the frequency pins that gets output by the Fourier transform. And we set the thresholds. So basically for the first 32 pins, we set the threshold value of 100 because we don't want them to have more energy than that. And then for the rest of them, at the higher end of the frequency spectrum, we set it to -1 to skip them because we don't necessarily care what happens in the higher end of the frequency spectrum. We just care that the lower end gets filtered out, as is the job of the high-pass filter. Then, and we feed this to another matcher that I wrote, which is called audio buffer check max energy and check max energies. And what this does performs another FFT for the buffer and then checks the passed list of maximum threshold values to ensure that we indeed don't have too much content in the lower end and to make sure that we have actually filtered out the content. Okay, so this was the characteristic type approach. But what if we know exact output of the filter? And we actually know because this is a really simple filter that doesn't do any special processing. It just filters out some of the audio. So we can actually do it just like this, where we read a buffer from file. This is another helper that I wrote. So basically, there is helper that writes to a file and reads to a file. And you just give it a pointer to the buffer and name of the file. And you can just push it there on a separate run. And then on the next runs, you can just read it there and check that these two things match. So that's definitely a lot simpler approach if you know exactly what you're trying to get out of the system. And that's it for the filtering tests. Next one that we have is the parameter tests, where we test the wet parameter of the software. Because there is a bit of one wet parameter. It's the only parameter that we have in this filter. And we verify with this that the parameter has some effect on the system. And when we check, again, back to the code. This is a bit long one. But basically it begins just the same as before. We create our plugin processor class and then another helper that I wrote for this project, which creates an audio sample buffer, basically a buffer filled with noise. And these types of short impulses are easy to test, and they're also good to test for other types of projects, other kinds of plugins as well. And yeah, create a MIDI buffer, prepare to play, process the block, because this block has the size that can be processed in one process block call. And now what we do next is that we check that these don't match. And what we do here with this test is that we test the default value of the wet parameter, because by default we want the filter to filter out the content. But how to get the parameter and set its value? Well, it's quite basic JUCE code. So if you've programmed with JUCE, this is definitely a familiar thing to you. You get the parameters, and then you get the single parameter, and then you set its value. And then, well, we create another buffer and call another process block. And this time we want to ensure that the two buffers match, because we have set the wet value to 0. And we expect them to be same, so that the wet value actually has some effect on the system. Then just for the sake of completeness, we set it back to 1 and ensure that the value indeed again changes. Okay, that's quite good. I could actually run the test. I didn't run the previous test, so that parameter demo, you can almost guess what it's going to look like, but I cannot write. Classic. And I was supposed to have 0 issues with this demo, and yeah, so in the end, it did the 3 assertions: the initial value test, the 0 value test, and the 1 value test, and they all passed as expected. I still have some time, so let's get back to the presentation and into the matrix. So how many times have you ended up in a situation where you stare at the meaningless numbers, not quite understanding what they mean, knowing that you kind of should, or they contain some crucial information? I have ended up in this situation surprisingly often. So for this, I created also image processing helpers for this filter unit test repositories. So we can just do the FFT and drawing of the results as part of the unit tests to ensure that our unit tests are behaving as we are expecting. So we can draw out these images during the testing. So here we can see again our familiar friend sine sweep, and here we can see it after filtering. It was quite an aggressive filter, as it seems. But yes, drawing things like this during unit testing can help you to sort of figure out if you are doing something wrong in your tests or if something else is going wrong. Then next slide. This is kind of a situation where we all want to be in. So all you can eat buffet, basically eat whatever you want. And in programming, it would really not be really nice to be in this situation where you can program anything and as much as you want and as many features as you want and not care for much what it does. But this has the unfortunate side effect of introducing latency. And from what I've heard, the audio applications, especially the plugins, tend to be a bit time-critical things. So it's good to have a bit of constraint there. And for that reason, Catch 2 provides simple benchmarking tools. It doesn't provide full profiling tools. That would be another good topic for a separate talk, definitely. But yeah, you can, as part of unit tests, you can also run these simple benchmarks to ensure that your processing doesn't take too long. I don't think it's fully comparable to actually running a VST and then running it as a part of a unit test. But it gives you a sort of a rough ballpark idea of what's going on. So if your process block function suddenly takes 3 times longer than it did, you may want to reconsider what you're about to do or commit. And in summary, we're approaching the end. The audio application should be tested like any other software, as expected. And there are a wide variety of tools available. Like mentioned, there was this JUCE unit testing, which may be good for simpler cases. Then there was the Google test, and then there are Catch 2, and well, there are quite a plenty of unit testing frameworks available. But templates like Bumble Juice, my mic is escaping. Almost got to the end without a problem. So, can get you started, and I think there are other ways of doing this. I wonder. This was a difficult thing to adjust in the beginning, and this seems to be still difficult. Can get you started. So yeah, I recommend if you can find a good template, stick to it. And yeah, FFT is a useful tool when doing unit testing as well. It's useful in many regards, but unit testing is not an exception. But I talked a lot about FFT in this, and it's definitely not the only tool. And in a sense, it's not. I'm not sure if it should be the to-go tool, the one that you try first, because as shown before, it has a bit of a non-exact nature. So if you can atomize your tests into smaller units and reduce the amount of randomness in tests, that may be a better approach. It depends on your use case. But on the other hand, if you are doing high-level testing, where you are trying to test a whole bunch of functions at a time, and in that case, you may not know the exact values of output, so it may be useful in that kind of characteristic testing. And the filter unit test project can contain useful resources and examples in getting started. So I'm hoping to improve it over the time. As mentioned, it's still a bit under construction, but it's getting better. And that's it. We reached the finish line without passing out. Wonderful.